Hello, welcome back. In this lesson, we will learn about hash functions. The security of blockchains requires cryptography, and the most used cryptographic primitive in this environment is a hash function. The purpose of hash functions is to create a kind of digital summary, or fingerprint, of some data. When I say data, I mean a collection of bytes, which can be a file or encoded text. Hash functions transform an arbitrary sized input into a fixed sized output in a deterministic way. The size of the output depends on the hash function used. Currently, the most commonly used cryptographic hash functions have an output of 32 bytes. As mentioned, the input is arbitrary in size. It can be a 10-byte or 10 megabyte file. The output size is independent of the input size. One of the properties of hash functions is that they are deterministic. That is, the same input will always generate the same output. Different inputs can generate the same output or different outputs. In general, we want different inputs to generate different outputs. As the hash function is deterministic, it generates a kind of fingerprint of the input file. The problem with hash functions is the possibility of collisions. As the input size is arbitrary, there are more possible inputs than possible outputs, which makes collisions theoretically unavoidable. Collisions occur when different inputs generate the same outputs. This is precisely what we want to avoid when using hash functions, so that each file has a unique fingerprint. Cryptographic hash functions, which we will from now on just call hash functions, are hash functions that are collision resistant. That is, two different inputs must not generate the same output. Let's make an analogy with the fingerprint of people. Two different people must not have the same fingerprint. Theoretically, avoiding collisions in hash functions is impossible, but we use hash functions whose collision probability is tiny. While avoiding collisions is theoretically impossible, collisions have never been discovered for the most commonly used hash functions. Once a collision is found in a hash function, the hash function will be abandoned and replaced with another considered more secure. Another critical feature of hash functions is that they are not invertible. The output is calculated from the input, but the input cannot be calculated from the output. This should be an expected behavior as the input can be larger than the output. That is, the fingerprint does not store enough information to retrieve the input. In addition to not being invertible, hash functions must be such that the fingerprint does not reveal any information about the input. That is, only having the fingerprint, it should not be possible to find the input by any method other than brute force, which means by trial and error. One use of hash functions is to prove that you know some information without revealing anything about that information. Let's look at the pattern of commitment and revelation. In it, you commit to some value, without informing the value. Instead of presenting the value, you commit to it through its hash, which must be presented. At the time of the reveal, you present the value. Then someone just computes the hash of the value to see if it matches the hash you committed to. If the hashes are the same, it will prove that you committed to that exact value. Examples of hash functions are MD5, Ripemd 160, SHA-256 and Kekek-256. SHA-256 is Bitcoin's most used hash function, while Kekek-256 is the most used hash function in Ethereum. 256 is the number of output bits of the function, in this case, 256 bits, which is equivalent to 32 bytes. MD5, whose output is 16 bytes, is no longer considered secure. It is an example of a hash function where collisions have already been found. A use case for hash functions is data integrity. Let's say you created a software, and you want to distribute it. You can distribute it on your server, but others may also want to distribute it on their own servers. How can people know that the software the other servers are distributing is identical to the original and has not been modified? To do this, just publish the software hash. So anyone downloading the software on another server just computes the hash and checks if it equals the original hash. If they are the same, it is proven that the software is original and has not been modified. As already mentioned, hash functions are everywhere in Ethereum. Remember that the ledger is a block structure, and the blocks are cryptographically linked. Now we can understand how this connection is made. Each block holds a reference to the hash of the previous block. If any block is tampered with, its hash will be modified, and the chain will be broken. A block's hash is its fingerprint, and guarantees its integrity. As with blocks, transactions also have a hash, which identifies them. When we want to find out if a transaction was executed on Ethereum, it is its hash that we look for, sending a JSON RPC request. We will see how to do this throughout the course.